All right. So we've got a GCF in here of t to the 7th, right? Okay. Now does 3 divide 125 evenly? No. Okay. So it goes into 12 evenly 4 times, but not into 5. So the GCF is only going to be the t to the 7th. So we're going to factor that out. And that's going to leave us then, remember, factoring is just division. So if I divide each of these by t to the 7th, I'd be left with 125 t cubed minus then 3, right? Equals 0. Now, this is going to be t to the 7th is equal to 0. Or, now it's not the square root method, but this sets itself up for like the cube root method. Okay? So 125t cubed minus 3 is equal to 0. There is one other, and maybe we'll mention it here briefly in a moment. Get rid of this thing. There we go. There is another rule that we can use to deal with things that are to the third power in regards to like differences and sums and stuff like that. You guys remember talking about the rule for difference of perfect cubes and the sum of perfect cubes? We'll talk about that in a minute then. Add 3 to both sides here. So I get 125t cubed is equal to 3. I'll divide both sides by 125. So we get t cubed is equal to 3 over 125. Then I'm going to take the cube root. So I'm taking the cube root. Okay, it's not a plus or minus. Okay, it is simply just the cube root of whatever you have here. Okay, so I get the cube root of 3 over 125. Well, we know based off of our rules for radicals that we rewrite that as the cube root of 3 over the cube root of 125. Does anybody know what number I multiply by itself 3 times to get 125? 5. So I get cube root of 3 over 5. That's one solution. The other solution over here, take the 7th root of 0, and you just get 0. Just be careful because there is, when you type it in, there is a difference between cube root and square root. So when you're grabbing, I don't think I can get the little tab that shows up over here. There should be one that has like a should have like a box, and then your root, and it should have a box on the inside. It should look something like that. That's the one you want to choose, and you got to put a 3 out there to tell us it's a cube root. Does that help? Anything else? 33. Okay. Let's see here. Copy. So here we're looking to find all real solutions of the equation. First thing I want to look at this and say that it is kind of that structure, right? It's quadratic in form. We've got a relationship between that exponent there and that exponent right there that is the same as if they were 1 and 2. Okay, so it's a 1 to 2 ratio with those exponents. So what we can do is the U substitution technique. So we're going to let that thing right there be U. So we're going to let U equal x to the 2/3. Then U squared is going to be that squared, which we talked about. The reason we do this, obviously, it might not be 100% needed, that line there, but what's nice about that is that if I take U to be x to the 2/3, then U squared has to be that x to the 2/3 squared, right? And if I evaluate that, it gives me x to the 4/3. So it allows me to make the jump, make the connection that U squared is the same thing as x to the 4/3. So then I look at that, and I can replace not only that with U squared, but I can replace this with U, and it's going to get rid of all my x variables and rewrite the entire thing in terms of U. So that is going to get replaced with U squared. It'll be then minus 14U, and then plus 48 is equal to 0. My factors both have to be negative here, because they're going to multiply together, give me a positive, and add up to give me a negative. What are they going to be, though? Good, -8, -6. Okay, so this one's going to give me U to be 8. This one's going to give me U to be 6. Working through that, then now that I've got what U is, let's back substitute. So remember, U was x to the 2/3, so we're going to replace that back in. So x to the 2/3 is equal to 8, and x to 2/3 is equal to 6. We talked about two different techniques yesterday for eventually solving these for x. We'll do one technique with this one, and we'll do the other technique with this one, so we get a variety. The first technique we talked about yesterday was, if I've got x to the 2/3, I'm solving for x to the first. So what I'm going to do is I'm going to raise that to the reciprocal power of 2/3. So it ends up being 3/2. And that's going to be x to the 6 over 6, which is just x. And then here I'm going to do the same thing, and I get 8 raised to the 3/2. Now, understanding what 8 to the 3/2 means is this 2 is our index, meaning that becomes the root that we're taking. And then we get 8 to the 3rd. Okay? So 8 to the 3rd, is it 216? No, 512. So square root of 512. Okay. 16 and 4, 16, 16. Yeah, that makes sense. So this is divisible by 256, isn't it? And 256 is a perfect square. So this goes to, just working this out, this goes to 256 times root 2, right? But 256 is a perfect square. So 16 root 2 is one of the answers they're looking at. And now I've kind of neglected this, but it's plus or minus, isn't it? Always got to remember that. So plus or minus 16 root 2. Okay. And then this one over here, like I said, we can do this one a little bit differently. I guess it might look different the way we structure it, but it is exactly the same logic. It's the same algebra. We're just doing it at a different step. X to the 2/3 really means the cube root of x squared, doesn't it? If I want to isolate the x, then here I can cube the right-hand side, or sorry, left-hand side, and cube the right-hand side. So it gives me x squared. Okay. 6 to the third, that is 216. And now I'd square root both sides. Okay. So 216. We got perfect square in there of 36, obviously. Just the 6 times 6, right? That gave me 36, and then times the 6 gave me 216. So I know 36 is in there. So that's going to be root 36 times root 6. So that simplifies to plus or minus 6 root 6. Is that all right? A lot of square root, cube root, that type of thing, understanding throughout the course. Okay, so the course is going to incorporate us having that ability to use our exponent rules to navigate through particular problems, and it's not every single problem. It's kind of hit and miss. Okay, every couple sections might incorporate a heavy use of radicals and laws of exponents, that kind of thing, and the next couple sections might not, and then we get to a couple sections that do. So it's back and forth throughout the year. If you struggle with radicals and those types of things, let me know, and I can point you to some resources that are going to help with those rules. I had a question about, I think it's 29. Okay, so if I pull up 29 here, and we'll just work through it. I don't know if we'll get through the whole thing or if we'll go through the whole thing, but just want to make a point here. Now the question says find all real solutions. Okay, and that's something to kind of think about as we're doing this. I look at that and I think, okay, it's not a quadratic, but it is quadratic form. So I'm going to let u equal x squared, then u squared will end up being x to the fourth. I'm going to replace that, so I get 2u squared plus 7u plus 4. And I look at that and I say, okay, well, nothing factors out. There's no GCF there. Okay, 2 won't divide out of everything. So I try AC method, which gives me 2 times 4 is 8. There's nothing that multiplies together to give me 8, but adds up to give me 7. So what do I have to turn to here when I want to factor that thing? Got to go to this, right? Quadratic formula. Now, and this is the thing that I think a lot of times we neglect, we don't pay attention to, because in the past, algebra 1, algebra 2, it was always an x. So we just ignored it, and we just apply the right-hand side, and we know that that's solved for x, right? Well, my variable right now is not, because I introduced u, my variable is not x. My variable here for 2u squared plus 7u plus 4 is u. So the quadratic formula is solving for u here. Does that make sense to everybody? So if I do this, just plugging this stuff in, I get negative 7 plus or minus, so it'll be what, 49 minus 4a times c all over 2a, and that ends up being u. So let's just simplify that real quick. Negative 7 plus or minus. So 49 minus 16. Okay, so I'm going to get 33 underneath here all over 4, which is great. That's fine. But remember, that is what u is, right? So let me Let's just cut this and move it real quick. Say again? Oh, my fault. So, okay, thank you. So this is 4. So I did 4 times 4, got 16. So it's 32, right? So that gives me, what, 17 in here? Thank you. But that's u, right? Okay. What was u? U was x squared. Okay. So if I get this replaced with x squared, okay, how do I solve for x? I take the square root, right? So this is going to look like x equals square root, so it'd be plus or minus. Now it'd be negative 7 plus or minus root 17 all over 4. Now we can kind of clean that up a little bit. Negative 7 plus or minus root 17 all over 2. You guys agree with that? Now I'm going to rewrite this in 2 versions. I'm still going to go plus or minus. But now I'm going to go negative 7 plus root 17 over 2. And then I'd have plus or minus negative 7 minus root 17 over 2. Does that kind of make sense, everybody? There are still, so there's 2 solutions here now because of the plus or minus. There's 2 solutions there because of the plus or minus out front. But I want to talk about these. Think about this part right here. Okay? And that radical 17. Radical 17, a little bit bigger than 4, right? What's negative 7 plus something a little bit bigger than 4? It's pretty close to negative 3, isn't it? Okay. Well, if I take square root of negative 3, what kind of number is that? It's imaginary, right? Got to bring in I. So do I get any real solutions from that first one? No, because that radicand and that numerator is negative. Okay. Look at the other one. Okay, now it's negative 7, and now I'm removing more from that. Okay, so negative 7 remove more is a bigger negative number, right? So again, in that second one, I get imaginary solutions there. Okay, so just be careful. Even though you did all this work and that's right, make sure that you pay attention to how it asked you to write the question. Okay, it wants real solutions, so there are none. So you should type in no real solutions. Okay. Eventually, guys, when we get there, it'll be a while, but there will be a need for us to be able to come up with these 2 solutions. Okay, towards chapter 4, they will ask us for those 2 solutions. But right now, the discriminant essentially tells us no reals. Is that all right? Okay. Is anybody having trouble with? I think it's like 18. Yeah? Like this thing? Kind of ugly. Several different ways you can do this. So this is the last one from the homework today that I'm talking about. So we can get into a little bit of the absolute value stuff, which isn't very difficult. But that right there is, on the left-hand side, we've got a compound fraction. Okay, multiple fractions inside one another, right? It's a nasty, ugly equation. You can do a couple things. If you want to, and it's messier this way, but you can take this thing here, and you can rewrite that as one fraction. So come up with a common denominator, which would just be x. So you write this as x squared over x plus 6 over x. So then you write it as x squared plus 6 over x, right? Does that make sense? Maybe that might actually turn out to be a better route. Let's try that. So LCD, would be x. So we're going to multiply that by x, right? Oh, x over x. So that's going to give me x squared over x plus 6 over x, which that's going to then lead to x squared plus 6 over x, right? Is that okay with everybody? Now, if I do the bottom, it's a similar thing. The LCD on the bottom, again, is x. Okay, so you want to multiply by x over x. Does that make sense? So it gives me 8x over x plus 3 over x. That's going to lead to 8x plus 3 over x. And that's what the left-hand side looks like right now, right? Which is fine. It's good. Okay. If I have a compound fraction like that, and now I've condensed it so where I got one fraction on top of one fraction, like if I had like 1/2 divided by 2/3, you ever remember how we would do that actual division? You do that, right? Okay. Can I do that here? Yeah. Okay. Think about this though. Let's look at the uniqueness between that denominator and that denominator. They're the same, aren't they? Now I say the uniqueness because in every problem they might not be the same. But what if I had like 2/3 over 4/3? Let's look what that turns into if I apply this rule. Don't the 3's cancel out and just leave me a 2 or 4? Does that make sense? So if I were to just wipe the 3 out there and the 3 out there, it leaves me with 2 over 4. Does that make sense? So you can do that. So here, because those denominators are the same, I can either just cancel them out and be left with x squared plus 6 over 8x plus 3. Or if I wanted to kind of invert that bottom one, if I reciprocal that bottom one, multiply it by the blue one, it's still going to give me x squared plus 6 over 8x plus 3. Okay, so that's just condensing the left-hand side. I really haven't dealt anything with the equation yet. We just transformed the equation to x squared plus 6 over 8x plus 3 is equal now to 4x, right? If I have a fraction, I want to get rid of that denominator, right? And multiply both sides by that denominator. So we get x squared plus 6 equals 4x times 8x plus 3. So at this stage, guys, then it just turns into that. And I'll let you kind of finish this, but it'll give you 31x squared plus 12x minus 6. And what you're going to have to do there is use the quadratic formula. It turns into a real ugly set of coefficients. And you need to turn the quadratic formula. That's an option, okay? Now, here's the one thing. At any time, because the way the question started, okay, you cannot have 0 as a solution. If at any time you do the work and you get 0 as a solution, plug it back in there. Don't I hit 6 divided by 0? And you can't do that work, right? Okay. There's another situation, okay, where this value here cannot end up being 0. Okay. So what I would need to be able to do, and I don't think it's going to happen to us, but I would need to say, okay, if 3x is equal to negative 8, so then I get 3 is equal to negative 8x. I need to make sure that I don't get an answer that is negative 3/8. So if I plug in negative 3/8 right there, that's going to give me 0 in that bottom fraction. Therefore, I could not do x plus 6 divided by x divided then by 0. Does that make sense? So you just got to be cautious. That's one thing that people neglect. They go through all the work, they know the algebra, but then they forget the logic of what our answers are saying, what our original algebra was saying. We can never divide by 0, so we got to check that. That's one approach. Okay, and I know my work here is kind of everywhere. That's kind of messy, but what if I did this? Can I multiply this side here by 8 plus 3 over x? Cancel that, come over here, multiply by 8 plus 3 over x. What that's going to do is give me x plus 6 over x is equal now 4 times 8 is 32. And now 4x times 3 is 12x, but it's over x. So it's going to give me 12, right? Still got a denominator here of x, so let's go through and multiply everything by x to get rid of that. Does that give me 31x squared plus 12x minus 6 again? And you see there, that's quicker, right? Okay. And now when I show two methods, or we do two methods, or three methods, or four methods, people are like, oh, that first method was useless, I'm never going to use that. Well, down the road, guys, in other algebra, that first step might be critical, or that first technique might be useful to us. Does that make sense? Where this one maybe doesn't maybe present itself. Okay. So as we learn multiple routes, I know some people say, well, I'm comfortable with this route, I'm going to ignore it. Okay, I'm not going to pay attention to route 2, route 3, route 4. And I was that person when I was in high school. I was that person when I was first year in college. I understand how to do it my way. I'm going to do it my way and only my way. And then I started to find out, oh, my way isn't always the best way. Okay, so the more ways you can learn, one, it makes you understand the system a lot better of mathematics. But two, it opens the door to you being more efficient. Is that okay? Just briefly, guys, because I think this is something that we have some experience with. Let's come to these last few equations inside these notes. Just talking about absolute value equations. The next couple of days, what I want to talk about are absolute value equations, absolute value inequalities, and then linear inequalities. And actually, we're going to talk about absolute equations first, then we'll talk about linear inequalities, and then we'll talk about absolute value inequalities. All right, so this is 30.
Wait, that's 30?
Yeah. So this is quadratic in nature. We need to do this one?
Let me check. Yeah, we're fine.
Okay, we don't need to do 30, so 18.
I just don't want to do the quadratic formula. 18, 19, and 24, 26.
All right, so 18, 19 is the same question.
Did you say this isn't due tonight anymore, is it?
No, I give one more day on it.
Yeah, why did you send us 6 for it?
Oh, except for
Just getting them up there, getting them ready.
Yeah, we have one more
I
one.
don't know how to do it. You didn't know.
Don't worry about the new ones that I've added.
Promise?
Yeah. Okay, so we've got that there. So this is number 18 and 19. There are two ways of doing this. How do you want to do it?
First way, easy way.
The easy way.
Okay, I'm going to show you both ways. Because when you pigeonhole yourself into only learning one way to do something,
I do what?
okay, when you force yourself only one way, don't give yourself 2 ways or 3 ways, something like that, and you say, even though Mr. Fay shows 2, 3, 4 different ways of doing something, I'm going to grab my way because my way it makes most sense to me, whatever, I like it the best, it's the fastest. We go down the road a little bit and we come to a different type of problem, and we need to use aspects of the other techniques that I've tried to teach you, but you refused to learn because it wasn't your way. Does that make sense?
Yeah.
So try to show you concepts that are legitimate, that work, and it'll make our understanding of math easier. Okay? And that's what my goal is for us to understand the system of mathematics instead of being able to understand specific problems. So if I force myself to just understand and learn how to do specific problems, how many problems are there? There's an infinite number of problems, right? I'm never going to be able to learn how to do every single type of problem if I focus on just being able to solve problems. If I focus on trying to understand mathematics, then I open the door to being able to solve every problem. Because I can change my methods and my techniques and adapt using appropriate rules to address anything that they throw at me. Does that make sense?
Yeah.
Okay. Let's kind of teach a man or give a guy a fish, feed him for a day, teach him how to fish, feed him for a lifetime, right? That's the idea, okay? So, if I look at this, funny story talking about fishing. My parents' neighbor, he's an older guy. He's got a cat. He loves this cat, but he's an older guy, and so cats don't like to stay home, right? They like to wander. And this cat comes to my parents' house all the time and just hovers underneath their cars. So this guy, he's got a big fishing. He's like 75 years old. He's got this big fishing net, and he's catching his cat with his fishing net. And he catches it, and he just walks home with it over his shoulder. It's the funniest thing you've ever seen. All right. So we've got this equation. 2 ways to do it. Let's do it the hard way first. Maybe not the hard way, but the long way. Is that okay, Chuck?
I thought everyone instantly stopped taking names after that.
That thing right there. Okay? Compound fraction. Maybe sometimes called a complex fraction. Pretty ugly. Let's condense this. So this algebra, guys, is going to be essential for us when we get to trig. Okay, that's kind of why I want to show this. We need to be able to do this version of the problem in trigonometry. Okay? Let's take this numerator and just focus on the numerator. Let's condense that down to 1 fraction, because right now it's 2 fractions. Would you agree with that?
Yeah.
Okay? Let's condense that down to 1 fraction. So if I did that, what do I need here so that I can condense this into 1 fraction?
Say, Chuck.
I need to do that, right? I need to multiply this one by, the LCD is x, so I need to make this x on the bottom, so I need to multiply the top by that as well. So it turns in this. So that turns into just x squared plus 9 over x. You guys agree with that? Okay. Let's do the same thing for the bottom. That needs to become an x, so I need to put an x up there, right? Through multiplication. That turns into 5x over x plus 7 over x. So 5x plus 7 over x. Huh? Like so if you had 5 plus 7/3, something like this, right? What we started with? Because that's all x is, right? Is a number. Wouldn't you need to make that a 3 there and this a 15 up top? That's all I'm doing right here. I'm multiplying by an x over x so that I can condense those 2 fractions into the 1 fraction. This thing right here, okay, doing that, I think is a good thing to be able to do if you are uncertain about rules on how we add fractions with variables and that kind of stuff, and getting like denominators and all those processes. Restart what you're working with, but instead of using x, put in a specific value, and then think, okay, if it was just integers, how would I go through that math? Okay, and try to keep track and develop an understanding for that, and then say, okay, well, going back to x just represents a number, so do the same thing. Treat it the exact same way. Blaze?
Where did you get the?
Well, I was giving an example. So
Okay, no, you're good.
you're fine. You're sure?
Yeah, I just didn't know that.
So I was starting off with just this bottom here, and I wasn't sure how I can get to that. But if I put this as 3, what would I do if that was a 3? I had 5 plus 7/3. Well, I'd make this 5 over 3, right? Well, I can't just put that over 3 because it's not 5 anymore, so I need to change the top to 15. 15 over 3 is still 5 now, right?
Yep.
And then I can condense them into something like this. Okay, so now this left-hand side is actually x squared plus 9 over x divided by 5x plus 7 over x, right? That's equal to 8x. Now, this side here. That's a fraction divided by a fraction now, right? So if I had like 1/2 divided by 2/3, how would you do that? You'd multiply by 3/2, right? And we really multiply both by 3/2.
Yeah.
But we just usually just say we cancel that one out, flip it up here. So can I do that here?
Yes.
Okay, so it's going to turn into x squared plus 9 over x times x over 5x plus 7 equal to 8x, right?
Yeah.
When I multiply like this, okay, let's say I just had 1/2 divided by 3/2. When I flip that 3/2, it becomes 2/3 up here. What can I do with that 2 and that 2? Cancel them out, right? What can I do with that x and that x? Cancel them out. So when I multiply, I'm going to get x squared plus 9 over 5x plus 7 equal to 8x, right?
Yeah.
Okay. Now, so what we've done, guys, is that this original problem right there, that thing right there, this is an equivalent form of it. How can I be sure of that? Take a number like 1 and plug it in. I plug 1 in up top. I get 1 plus 9, right? I get 10 up top. Plug it in the bottom. I get 5 plus 7, which is 12, right? So I get 10 over 12. Put it at the bottom. Plug in 1. What's 1 squared? 1 plus 9 is 10. Plug 1 in the bottom. What's 5 times 1? Plus 7? 12. So we get 10 over 12, right? So I can check periodically as I go through the problem, I can check using consistent values of x to see if the work that I've done still produces the same thing I started with. Does that make sense? And that's kind of something to think about. Go up to go to Ford and look at them assemble a car. Are they going to assemble all parts of that car before they test it? They're going to put the whole car together and then turn the key and see if it works? No, they do quality control checks. Okay? After every stage of the assembly line, they check to see if what they just did is going to work. And if we check at every stage, then I'm guaranteed when the car is complete, I put the key in, turn it, it's going to start, it's going to run right, correct? Okay. Maybe not guaranteed, but I have a higher probability of it being successful than I do not checking it at all and waiting to the end. Okay? So mathematically, it makes sense to kind of do those things as you progress through the problem. Now, we've really just begun the question. Okay? Because we have not attacked this as an equation yet, right? I've just condensed the left-hand side to a better looking fraction. If I have fractions in an equation, how do I get rid of those? Multiply by the LCD. The LCD here is 5x plus 7. So we cancel there, leaving me just x squared plus 9. And on the right-hand side, I'll have 8x times 5x plus 7. So it's going to give me, what, 40x squared. 7 times 8, what's that, 56? X. So we can go 39x squared plus 56x minus 9 ends up being 0. Now I'm going to stop there. And I'll let you continue that on your own, but that's at that stage, 39, 56, and 9 are relatively prime to one another. Okay, 39 is a prime number. No, it's not 13 times 3, but relatively prime. So 13 and 3 are prime. So 56, 9, 39 don't all divide by something, right? So you have to use the quadratic formula here to solve for x. So I'll let you do that. Okay. Now we should have an additional approach. So let's talk about the additional approach. Okay. And it is exactly what we did here. We multiplied by the denominator here to get rid of 5x plus 7, right? Well, what if we just did that at the beginning? What if we, right here, multiplied by 5 plus 7 over x? And come over here and multiply by 5 plus 7 over x. What's going to happen with that denominator? Cancels out with that, right? Leaves me x plus 9 over x. Over here, 8x times 5? 40x, right? Okay, 8x times 7 over x gives me 56 x's over x, right? What's going to happen with those x's? Cancel out. So this gives me 56, right? So after one step of multiplication of that denominator, we get an equation like that. Still have a denominator though, right? Still have a fraction up there. Let's multiply by x again. Multiply this whole thing by x. What's x times x? X squared. It's going to give me 9x over x, which is just 9, right? It's going to be 40x squared. And that's going to be 56x. Set this equal to 0. It's going to be 39x squared plus 56x's minus 9. Is that the same thing that we have right here where my cursor is? Would you agree it's much faster that way? Okay, here's the thing though. When we get to trigonometry and the x turns into sine of x, okay, and the 9 is a cosine, and that 5 is a tangent, and the 7 is a secant, okay, and they've got those words in there. We can't use the approach that we just used. We have to use the above one, okay? So we have to have the ability to take fractions that are complex, condense them into essentially one fraction for trigonometry. So that was question 18. 19, same way. 25 and 26, or 24. Isolate the variable or the radical first. Did you do that?
Which one is it?
It's 24.
Yeah.
Did you subtract 6 from both sides first? Or that number, whatever that number is?
Okay, thank you.
And then square both sides. 26, the same idea. You need to move that to the other side. And then square both sides. Or move that to both sides and move the 13 over. It doesn't matter. But you need to get that thing by itself. You need to get the root by itself before you start applying the square.
Can you just add that, like, put, negative side, negative side of the way?
That's what I was thinking.
Yeah, so you can. I wish I could write on this screen, but I can't, so I gotta cut and paste it. So you can rewrite this as x equals 13 plus root x minus 1. Is that what you're saying?
Yeah, and then just something.
And then move the 13 over? Yeah. Oh, x. Minus 1. That's fine. Okay. You can add, to be honest with you, because when we are going to square it, you can actually just leave it this way if you wanted to. When we isolate the radical, if there's a multiplier out front, it doesn't matter if we move that or not. Okay? I guess remember the one. I think there was one we did an example out of 4 out there, and we left the 4 there when we squared both sides. This is just a -1 out there, so you can leave the negative there, square both sides, and still get the same solution. Let's do. I want to do. Did anybody have issues on 29? Sarah?
Can we do 26?
26?
Yeah.
Yep.
Okay, cool. You can't see it right in front of the audience, right? You just guess numbers playing it.
All right, so the first thing you have to do is isolate one radical symbol. You need to isolate either one of them, doesn't matter. So I'm just going to isolate the first one. So this is going to be root 16 plus x equals 8 minus root 16 minus x. If we don't do that, the next step will be, it will not create a situation where we eliminate a radical. So this stage here, once you isolate one, you then square both sides. So square that, square that. Okay. This is the reason we had to isolate. If I square this now, what's that side become? Just 16 plus x, right? Okay. On the right-hand side, now we have a binomial. So it's going to be 8 squared, which is 64. Okay. I'll multiply these two things together, so it gives me negative 8 times radical 16 minus x. And I'm going to double that, so it gives me negative 16 radical 16 minus x. And I'm going to square the last term. So a negative times a negative turns into a positive. And it's a 16 minus x. Okay. When we do that, guys, and I'm going to continue to use this rule, but we're doing a plus b squared. Remember, that's a squared. Plus then we multiply a and b together and then double it. And then we take b and square it. You remember doing that in algebra 1 and 2? So that's what I'm doing here. So now we got 16 plus x equals 64 minus 16 root 16 minus x plus 16 minus x. Now there's several things that people want to do here. I'm just going to be, I don't want to just blindly approach this and start merging like terms together, because I recognize that is positive 16 and that is positive 16. What are they going to do to one another? They're going to cancel. So I didn't want to merge that 16 with the 64. If I add x to both sides, I get 2x, right? Add that x to both sides. I'm going to move that 64 over. It's going to leave me negative 16 and then root 16 minus x. So I isolate the radical here, right? Now, like I said, you can move that 16 over. That's fine. What I'm not going to move the 16 over, but I don't want to square 16. I don't want to bring in 256 because it's just larger values. Do all of these numbers have a 2 in them?
Yeah.
Can I divide everything by 2? So x minus 32 is equal to negative 8 root 16 minus x. And now that I've isolated that, now I'm going to square that. Square that side, square this side. So give me x squared minus 64x. 32 squared, 1024. Okay. Now if I square this side, negative 8 squared is 64, right? Square the radical, and you're left with just 16 minus x. So 64 times 16, that's nice. What's going to happen with the 1024s? Cancel out. Add 64x to both sides, so we get x squared. Is that right? Add 64x. Yeah, that's right. So just get x squared equals 0. So x then in this case is just 0. For this question.
Yeah.
Okay. Now think about this. Let's try it. Plug in 0 here. I get root 16 plus 0 plus root 16 minus 0 equals 8. What's root 16?
4. 4.
So it does check out.
Question.
So everybody had the 16s were all the same number? So if you had 16 there, it was either like a 14 and a 14? You were 9, so you were 9 and 9s?
Mine were 9s too.
Okay. And then the number on the right was 6? Okay. So everybody's was structured the same way we got 0.
Question.
Yeah.
On the test, if I really look at it, I'm like, wow, that should have been 0.
I need work.
What you said?
I need work. On a test, I won't give you one like that where you can definitely see it. I will. So the structure there, everybody got 16 or 16, or 9 and 9, or 8 and 8, or the two positions where 16 are up there were consistently the same, right? Okay, and they were probably perfect squares, right? Okay. So by seeing that you're solving the algorithm that the computer wrote to generate multiple questions for people, I will change it so I can judge whether you know the procedure instead of the shortcut. Does that make sense to everybody? That's what I'm interested in. I'm interested in, can you isolate the radical, square it, isolate the remaining radical, square it, solve the remaining equation that's left over. Say again? Scroll down. What's the next one you want to talk about? Chandler, you said you had some questions. Did we answer them all?
We're thinking 32 over here.
16.
We don't need that one. We call the thing 32 over here. We get a chance.
Okay, so 16, we have a rational equation here, okay? If you had, let's say you had 10x over 26 is equal to 1. What would you multiply both sides by? 26, right? And you get 10x equals 26. Can I do the same logic with this? Okay, so the idea is, the way I got 26, I just plugged in 1 for x squared. Okay, so that is a number. So all I'm going to do, instead of multiplying by 26, multiply by the expression that when I substitute x, it gave me 26. So multiply that. Come over here and multiply that. Cancel. Cancel, so it leaves me 10x equals x squared plus 25, right? So I'll move the 10x over. So it's going to be x minus 5, x minus 5. So x equals 5 twice. You just have to type it in once, yeah. I don't know what it'll do if you put like 5 comma 5. I'd assume it counts it, but I'm not sure. Then you can check yourself. If I go up here, 10 times 5 over now 5 squared plus 25, does that still give me 1? Is that 50? Is that 50? This one here,
Oh, that's what I was talking about.
so this was 33,
Wait, no, that's like 32.
or 32. Would you agree that that thing right there is exactly the same as that thing right there?
Yeah.
So let's do this.
Oh.
No.
Because now, can I rewrite this as u squared minus 2u minus 73? Or 63?
Which way? Sometimes I think like you're smart too.
So u minus 9. It's probably because it's accurate. So u minus 9, u plus 7, right? That makes sense? So now I solve those for u, so I get u equals 9. And u equals negative 7.
Yeah.
But what was u?
X plus 7.
1 over x plus 7.
1 over X plus 7.
Okay, so now, good thing we went over question, whatever it was, what was the last question we did? 26, whatever?
16.
16. Because now these equations down here model what we did in the first step of that last equation. Don't we multiply both sides here by x plus 7?
Yeah.
Cancel, cancel. So it leaves me 1 equals 9x plus 63. Multiply here by x plus 7. It's going to leave me 1 equals negative 7x minus 49. So negative 62 over 9 is equal to x. And then over here, what we get? 50 over negative 7 is equal to x. The only thing you got to be cautious of, was there division in my original problem? If I come up here, there is division here in my original, right? What is the only number that cannot be put there and there?
Negative 7.
Okay, so I cannot have 0 in the denominator, and negative 7 would make those denominators 0, right? Were either of my answers negative 7? Nope, so we're good. Okay. Does that help?
Yeah, I thought this was so good. Good setup.
All right, I'm going to, so let's stop there. I'm going to add another day to this, so we'll have a little bit of time tomorrow in class. At the beginning, I'll get maybe about 10 minutes in the beginning class tomorrow to kind of wrap up any final questions that we might have over this.
Are we going to get time in class? Or we're coming right now?
No,